Compare these alarming numbers: 7,600 specific vulnerabilities, or CVEs, against over 729,000 total occurrences in the wild. This massive footprint is insecure design, OWASP's number 6 risk. With 35% coverage and a 6.96 exploitatable score, it's easily triggered. The paradox? Perfect coding cannot fix it. The tech industry relies heavily on automated code scanning tools to catch mistakes, but those tools only look at the code itself, blinding teams to structural, architectural flaws that leave a system exploitable by default. To understand exactly why this happens, imagine building a massive bank vault to protect millions of dollars in physical assets. You secure the front entrance with a state-of-the-art titanium lock. In software, this lock represents your implementation. It is the actual code you write. If you make a typo or forget to validate a user input, that is an implementation bug, a failure of the lock. But an insecure design is like building the walls of that exact same bank out of corrugated cardboard. The underlying architecture itself is the vulnerability. A smart attacker won't waste time trying to pick a perfect titanium lock when they can simply walk up and kick straight through the wall. Implementation is how you build the system, but design is what you are actually building. If your foundational blueprint is flawed, perfect code simply means you built a highly functioning trap for yourself. In the digital world, attackers routinely weaponize systems where the code executes perfectly, but the underlying business logic is broken. Take a major cinema chain offering a group booking discount through their mobile app. The developers built the feature exactly as requested, but nobody designed a requirement to collect a deposit upfront. A hacker maps out this business logic and writes a simple script to trigger it continuously. In milliseconds, they reserve thousands of seats across multiple theaters without paying a dime, locking out real customers and causing massive revenue loss. Consider retail sites selling high-end graphics cards that mysteriously sell out in half a second. The flaw is an architecture built with zero anti-bot friction. Prioritizing speed over verification, scalpers use bots to bypass standard queues and instantly buy the entire inventory, infuriating genuine fans. In both of these scenarios, no one hacked a database or bypassed a firewall. The systems were weaponized against themselves purely because they lacked basic architectural constraints. Then there are design failures rooted in concepts that are inherently insecure from day one. Consider the classic password recovery feature that asks a security question, like, "What is your dog's name?" This practice actually violates modern NIST security guidelines. It doesn't matter how strong the database encryption is protecting that answer on the back end. The secret answer itself is public information, easily obtained by an attacker scrolling through your Instagram feed. Perfectly encrypting a publicly available secret is the digital equivalent of our cardboard wall. It provides a comforting illusion of security that immediately falls apart upon basic inspection. Fixing this requires developers to move past the popular idea of shifting left in the codebase and go all the way back to the pre-code planning phase. This starts with core secure architecture principles. First, keep it simple stupid, or KISS, because complex systems naturally hide vulnerabilities. Second, systems must be secure by default, meaning if a developer or user wants to take a risky action, they have to manually opt in and turn the security off. Next is no security by obscurity, meaning if a hacker decompiles your app, your security shouldn't vanish. And finally, minimize attack surface, which means shutting down unused ports so attackers have fewer doors to try. Adopting these principles forces security to become a mandatory structural requirement, rather than an afterthought bolted onto the end of a sprint. The practical way AppSec professionals execute this is through threat modeling. This is the crucial exercise of sitting down before a single line of code is written and asking, how would a bad guy abuse this? Teams use specialized mapping tools for this process. OWASP Threat Dragon helps visually draw out data flows to spot risks, while Amazon's AWS Threat Composer is tailored specifically for uncovering cloud-based vulnerabilities. To go further, engineers use predictive AI tools like StrideGPT to anticipate how hackers might spoof or tamper with the system, and frameworks like OWASP SAM to measure how mature a company's overall security lifecycle actually is. Because ultimately, security is not a plugin you install at the end of development. If your team isn't doing threat modeling in the planning phase, you are shipping vulnerable software by design.